All right, very good morning to all of us. Today we'll be going through on the theory workbook for electromagnetism. So let's look at question one first for section B. So in this case, they show an electric current flowing through a long straight wire, and they want you to sketch the magnetic field lines. So in this case, they show you that the current flows this way. So this is the current I. So if you use our right hand grip rule, the thumb showing the direction of the current, your fingers will show the direction of your magnetic field. So in this case, the paper top view is viewed this way here. With a dot, dot means that the arrow is coming towards you, so the current is coming towards you. So your thumb must point towards you, and then your fingers will give you the magnetic field lines. As you can see, the magnetic field lines are not equally spaced. As they are nearer towards the wire, they are closer spaced to show that there is a stronger magnetic field. And as you move away itself, there will be a weaker magnetic field. They are more spaced apart. Similarly, for the other side, now the current is going downwards. That means that you should see a cross in the middle. Use your thumb now point away from your face, that means into the paper. Your fingers will give you the magnetic field. Remember to draw the arrow. Similarly, more lines closer towards the wire, and the lines are spaced further apart when it's further away from the wire. Part B. Explain why the magnetic field lines nearer to the wire should be drawn closer. As explained, it shows that the strength of the magnetic field is stronger nearer to the wire. What is the method that you use? It's called the right hand grip rule. Okay. Question 2. Sketch the magnetic field patterns for the solenoids in figure 21.5 and 21.6. Label the magnetic poles. So in this case, what we have here are solenoids. Okay, so for solenoids itself, what we can do is to use your right hand grip rule also. There are two ways you can do. Number one, let's identify how does current flow. The current flow this way, flows this way, goes down, goes down, goes down, goes down, goes down. So you can, number one, use the right hand grip rule, use your fingers to follow and cup along the solenoid. That will show your thumb as north. That's the first way. So if you cup it around, okay, the fingers are going down, okay, and then your thumb will give you a north. So that's why here is north and here is south. Another way is how you take each of the coil. Okay, so imagine this is a coil. Take your right hand and use your fingers and grip around it. This is your thumb. Current is going down. Okay, so you use your thumb to grip around it. So this is the wrong direction. Your thumb should be at the bottom. Okay, so if you grip, because you must use your thumb to show the direction of current, your fingers will show the magnetic field. So in this case, it goes in this direction. So that's why north is still here also. So most importantly, when you draw your magnetic field lines itself, that it must be symmetrical, and there must be equal lines such as symmetrical. Okay, remember to draw your arrows. Make sure that no lines intersect. So similarly, from the other side, if you draw the current, goes up, goes up, goes up, goes up, goes up. Use your right hand grip rule. If your fingers are the current, cup along it, you see the north is here. If you use your finger to grip the wire, now your fingers will be the magnetic field. Your thumb is the direction of the current. In each of the coil, you can see the magnetic field will go here. So, okay, so it will go towards the north direction. So there are two ways to actually do it. Part B suggests three ways to increase the magnetic field strength. Number one, you can increase the current running through the solenoid. Number two, you can increase the number of turns so it becomes very dense. Number of turns in per meter per unit length is much more in the solenoid. Or you can use a soft iron core within the solenoid. This will concentrate all the magnetic field flux more towards the within the solenoid itself and will strengthen the magnetic field. Question 3. So now we're going towards the application of electromagnetism. In this case, it's a circuit breaker. It's used to cut off the electrical supply when the current is too large. So please take note that it's only when the current is too large that we cut off the electrical supply. So let's see how they make use of this mechanism when the current is too large to actually cut off the supply. So let's see, current flows here. So current flows here. Okay, so by right, current flows through here, comes up here, goes through here, goes here, and then contact then goes out. So this is the original path. But in the event we do not want the current to flow, what will happen is this thing will go out and there will be a break of current here. Break. Okay, so there'll be a gap here, the current cannot flow through. So let's look at the answer. Okay, let me erase all of this first away. Okay. So describe what happens in the circuit breaker when the current flows exceed the safety limit. It's only in use when the current exceeds the safety limit. So when the current exceeds the safety limit, the large current will cause the solenoid, this, to become an electromagnet, a strong electromagnet. This will then attract the soft iron latch here. So it then will be attract. What will happen is when this goes down, your spring will then push this thing out. This releases the spring and results in the safety bar being pushed out. And what will happen is this will break the circuit. So this is how your circuit breaker works. Okay. Explain why a soft iron is used for a latch. Why you don't use steel in this case? Because soft iron is a soft magnetic material. It is easily magnetized and demagnetized. Soft iron. Then you have to answer the question because it said explain. So I know that soft iron is a soft magnetic material. Hence, it can be induced to become an induced magnet easily when it's attracted by the magnetized solenoid. 2. Also, the soft iron latch is able to return to its unmagnetized state under normal operating conditions when the solenoid is demagnetized. So first you tell us that this is a soft magnetic material. What does it have? It's easily magnetized and demagnetized. At the same time, then you must explain how this magnetized and demagnetized is applicable in this situation. So you got to be explained in detail. Okay. All right. So with this is how we will end off for part 1 for the electromagnetism theory workbook.